Today we're going to continue our discussion on making things out of plastic. In previous module, you've seen a method which was very common to making things out of plastic, involved melting the plastic and then under pressure injecting it into a mold or a cavity, the shape or the geometry that we want, and we call it injection molding. Today, we're going to continue on our discussion with another process, which is called thermoforming. Thermoforming, unlike injection molding, we don't melt the plastic, but we get it to its glass transition, which you are familiar with it, a temperature where the plastic is soft and we can form it under pressure and heat. And that's the process which we call it thermoforming. Just as few examples to show you the things that are made by thermoforming, the things that I just use myself. If I can again return back to share my screen. All right, let's get there. Well, today, just as an example, I start my day with a cup of coffee, and you can see I got it from Blends. So the lid, most of the coffee lids, they are made by thermoforming. So of course, I drank it and I wash it. So this one is most of the lids are made by thermoforming. Then for lunch, I ordered a food and I got my food by Skip the Dishes. And then the foods was delivered in a package, 2 packages, which again, they are made by thermoforming. Thin plastic, and usually they are cheap and they are made by thermoforming. And then I had my dessert, and again, it came into a package which was again made by thermoforming. And this one, so if I push those away a little bit, this one, like even for clipping it, probably you've seen it somewhere, maybe for fruit packaging as well. So they can make sort of it in a way that the lids come with the main package as well, and they can fit like these clips nicely. And then later I had, some fruits, which comes into a container made by thermoforming. Well, up to this point, probably you think that, okay, I'm using a lot of plastic or I'm eating a lot of things. Well, this is just to make a story for today. Only one day a year, I consume so much plastic, and that's just because of teaching thermoforming. Anyway, and after eating so much food, of course, I need to entertain myself. And so let's get rid of these things. And then I wanted to play some video games. So I use my gaming mouse. This is the gaming mouse that I have. I'm not going to tell you what type of gaming I play. Probably by now you guess from the music that I play what type of movies that I watch. But I'll talk about the type of gaming that I play later. Anyway, the dust cover for this mouse is again is made by thermoforming. And most of the electronic packages, when you receive them in a package like this, if you notice, for most of them, like inside the cardboard package, you will see maybe another, let's say, container or something. And the way to make these things is by thermoforming. All right, I hope I convinced you that even in one day, one person, how many things are made by thermoforming. And later, of course, when I'm getting old and I need a pill, I don't know what is this one. Anyway, the packaging of most the medicine tablets and pills are made by thermoforming. Let's go back to the other slide. Okay, here. All right. But what is thermoforming? Well, basically we say thermoforming involves forming a thin sheet plastic using heat and pressure. This is a simple definition of thermoforming. And today we are going to analyze some parameters that involves thermoforming. So, but before I go further, is there any question? You guys are still with me? Or what do you think? You guys are using the same amount of plastic a day? That feels bad, right? Well, this is what it is. As I told you before, until we could, or human could discover a better material, apparently we stuck with using plastic. But later we'll talk about, when we talk about sustainability, we'll talk about it more. But today, let's just focus on these thermoforming process. So in the example that I showed you, and also in examples that you see here, like these trays or coffee lids and food packaging, one thing which is noticeable is all these things are made with very thin plastic, right? They are made by sheet, a plastic sheet, in fact, and the thickness are small. And maybe that's the main reason that instead of injection molding, we need to use another process, which is thermoforming. All right. Oh, sorry. I'll get to that one. So, for example, Lego bricks. We talk about them during injection molding. When you watch a video, most likely that all these bricks are made by injection molding, right? Injection molding. However, the base, like this one, cannot be made by injection molding. And do you know why?
It's too big.
Too big in what sense?
Too wide.
Too wide. So, or what Pure is trying to say, I guess, is if, let's say, we look at the like a regular base for, let's say, a Lego, they are, let's say, in range of meters or half a meters. So let's say for this one is 1 meter by 1 meter. And then the thickness usually is in a range of maybe 5 millimeters or even less. So as you can see, one dimension is significantly larger than others. Let me write it down here. One dimension is significantly larger than the rest. So, but what is going to do? I mean, when one dimension is larger than the rest, what sort of problem is going to cause us that we cannot use injection molding? Think about injection molding. We had a cavity, right? We melt plastic and we inject it into that cavity. Why we cannot make the base by injection molding? Can you think of any reason? We saw that the one attribute of these basically base is that one dimension is significantly larger than the rest. But why it can cause us not to use injection molding? Well, maybe I give you a hint. So first of all, looking at this, the geometry of this one, we can imagine if you start injecting plastic at 1 point or even few points, by the time the plastic gets to the rest of it, it's going to take times, right? And so we're going to experience non-uniform flow. Also, this process, if we make it by injection molding, requires extremely large pressure. So requires extremely large pressure. And we learned last week that it means when you need extremely large pressure, it requires a large clamping force. Remember the clamping force for the 2 halves of the molds, right? That's why we need to invent another process, and that's why we need to rely on thermoforming. Also, if we look at the comparing injection molding with thermoforming, if we compare the 4 attributes of thermoforming, like always, when we compare their attributes, so the 4 attributes, recall they were cost, rate, quality, and flexibility. How much does it cost to make one part by thermoforming? How fast I can make one part, and how good it is. How flexible is the process? Again, if I change the geometry, how easy I can do that? Well, let's say, as something to compare, if we have here injection molding, and over here, the new process, which is the thermoforming. So for injection molding, you saw the cost was extremely low, excluding the initial cost of the tools. The rate was super high. In fact, that's one big reason that make it so attractive. The quality relatively good, either in terms of the texture, the surface quality, the life, the strength, and also the dimensional accuracy is something that we expect from a plastic. It's something that we are happy. But the flexibility was super low, because if we change something, it means we have to go and change the mold, and it's expensive and not easy. With thermoforming, usually we have the same attributes. The cost is low when we have the initial molds, so we can produce at fast rate and low cost a lot of parts. That's why the coffee cup lids are made by thermoforming, because in a matter of seconds you can produce many at low cost and high rate. The quality is not as good as injection molding, so usually we put it in a category of low. And here by quality, we are referring more to the dimensional accuracy. But we make things usually with thermoforming that we don't care too much about, like the tolerance. And the flexibility, as you can guess, is super low because it involves a mold. And whenever it's something we're making involves a mold, it means any geometrical change and even material involves some changes. All right? Any question, guys, so far? All right, so silent, I assume that is clear. Moving on, as I said, a few examples, and I showed you other examples as well. We can categorize thermoforming to 3 main categories. Of course, there are many other also methods, but these are the three main, I would say, categories. Looking at these three schematics, so the first one, so this is the mold that we have. Look at the one on the left. So the mold is a positive mold. What do I mean by a positive mold? So something that stick out. Let's say I'm going to make maybe a cup. All right. So maybe I'm making, let's say, this cup. All right. And then the second one, the mold is negative. So a negative mold. And the third way, it has both positive mold and negative mold. So in this schematic, at the top on the left, this is obviously is the plastic sheet. So this is the plastic sheet. All right. And this plastic sheet, so it is under heat. So we have heat here to sort of make it flexible. And then when it gets to its glass transition, what will happen is we move this plastic sheet, which has been clamped at two sides, down to this positive mold. And of course, here we have a vacuum. Like on the image below, if you can see, we have a vacuum which creates a negative pressure. And this negative pressure usually causes this mold, this plastic, we can form it to even the smaller radius or a small complex geometry that we want. For example, on this container that I have, you can see it has some patterns on it. So the second one, now you can guess. This is exactly similar to the previous one, except here we have a negative mold. And this time, of course, we have the vacuum at the bottom. And so the plastic is being heated under heat. And then we have like pressure. Over here is going to be positive pressure. And over here, we're going to have negative pressure. And then we get to the form that we want when the plastic comes down to this negative mold. The third one, it has both positive and negative. And as you can then imagine, we push these basically mold, the positive mold, down and until it matches the negative mold, of course, considering the thickness of the plastic that we want, right? And then we get the form that we desire. So each of them has a name. So this one, of course, the one on the left, based on the mechanism we use, it's called vacuum molding. The second one is called pressure molding. Sometimes it is called blow molding, but blow molding, normally we refer it when we are making things like garbage bags, which again, you've seen in some videos earlier when you did the start quiz. And then the last one is called mechanical molding. If I ask you, which one do you think result in, let's say, a better part, which one you would pick? Which one result in, let's say, more accurate part, a part that has a better dimensional accuracy? Any idea? C, like the mechanical one? All right. So The rest of you guys, you think the same?
I agree with C.
So Kieran also agree with C. That's in fact, oh, go ahead, please.
No, I was just gonna say I basically flipped a coin to guess which one.
So, well, if you let's see between these three, I agree. C is more accurate. Why? Because the other two we rely on vacuum, and unfortunately this year you guys cannot use we have like some nice vacuum, basically thermoforming machines. And last year, students made their mask, their Halloween mask. This year, you cannot do it. So something that obviously they could see with vacuum, usually, if there are like very small features, you need super high pressure and you cannot get that accuracy that you want. And sometimes after releasing the pressure, then things may return back, at least in some areas, if you don't let it cool enough to the maybe return back, and so you don't get the accuracy that you want. While the mechanical one, so you use a press, you make sure that the positive and negatives fit to each other, and you get a more uniform thickness. So I would write this one is more accurate, or let's say better quality. However, it is more expensive, right? Because now instead of making one mold, you need to make both the positive and negative parts of the mold. Well, we talk a lot about getting to glass transition, but we never talk about how we can basically heat a plastic. It's obvious that direct fire is not a good idea, right? It's going to burn some area of the sheet plastic. The common method is convective and radiative heating, basically. And to do so, people use like heating lamps. And so radiative heating is the most common, which again, I have some, put some pictures here. From this website, you can check the price. For example, you can buy like this lamp. The price is not that high. You can check them. And also with each lamp comes the power, how much heat it can gives you in second per meter square. So that's what we call it power, or to be more accurate, power intensity. And we show it by P. So, and most likely you've seen in one of your physics course that we have a range of wavelength, like on this chart, as I showed here, we have like a range from 100 meters to 10 to power of minus 13 meters. For visible lights, so it is in a range of micron, the wavelength, something around here. And for heating is just a little bit before that. So usually this area over here is the wavelength which result in more heating and less light. And this is where most of these lamps has been basically based, and they gives us like heat based on infrared heating. So how much heat a plastic can get? Well, here we see basically the power, which depends on the lamp. Amount of heat we can get, Q, let's call it Q, is equal to P multiplied by A. P, of course, is the intensity, but what is this A? A, we call it the heat absorption coefficient. Heat absorption coefficient. And physically, it means how much heat a material can absorb. how good it is. So for example, you know, a black material can absorb heat way better than white material. So this A, we can say that depends on many things, on color, for example. It depends on materials property. Some materials can absorb heat better. It depends, we can say, on density. The more dense the material, they can absorb and hold the heat better. We can say it depends on CP, the heat capacity that you saw the definition last week, and many other things which you can find them on the internet. So this A, then let me put it on these so we know what we are talking about. All right. For plastic, this number is in a range of, for plastics, A is in a range of usually 0.6 to 0.9. For example, for one type of ABS, for white ABS, A, I believe, is in a range of 0.8, I guess, if I'm not mistaken. All right. So, and of course, you know, the bigger this number, the more heat in a shorter amount of time a plastic can absorb. Okay. So that's easy and it's obvious. Sorry, that's my phone, but I can ignore it. All right, now let's get to the some engineering analysis of thermoforming. In particular, we need to answer two questions. First of all, we need to know how much we need to expose a plastic sheet to heat. So this is the time that we need to figure out. Like exposure time. And also, it's obvious how much we can stretch a plastic. Of course, you cannot have, let's say, a square piece of plastic of, let's say, 10 centimeter by 10 centimeter and stretch it to make containers of 1 meter by 1 meter, right? Let's say big containers of 1 meter, 1 meter, and 1 meter at the high. There must be a limit. So we need to, when we design a mold, we need to know how much we can stretch. So how much we can stretch and how long we need to basically expose it. Again, a good example, last year, students, when they wanted to make their mask, they had to calculate how much they need to hold the plastic sheet. They had the information for the lamp, how much power the lamp has, and also basically the thickness of the plastic, the material. They need to know how much they need to hold it. Otherwise, if you expose it to heat a lot, it's going to melt, and that's bad. And if it's not exposed enough, then it's not going to be soft, so you can form it and get the desired shape that you want. And also, it's important to know that if you design something, like again, there were some examples where the plastic like sort of teared because of because it was stretched too much. So we need then to quantify those, and we find out sort of a formula. So next time, if we are using a thermoforming machine, we can do the calculation. Well, these are the suggested temperature range for each of these material. Again, for different material, you can find them find on the internet or in your textbook. For example, for polystyrene, the recommended range is around 135, 140 or something. For ABS, you can see it's a little bit higher. And for PVC and PP, these are common materials, you will see the range of the temperature. And this is basically the glass transition, we say, but in a range, in fact. So if I draw the, again, a stress strain diagram, so let's say over here it's my stress, and here is a strain. So we know at room temperature, plastic is usually brittle, and after that elastic zone, it breaks, and then we get to like a close to melting point. It's very soft, and then breaks, something like that. So we saw there is a point when that we can observe a large, basically drop in modular plasticity, and this is where what we call it a glass transition. This is a range which our TG is there. The TG, the glass transition. That's why we see a range of temperature. All right. So, but the question that we try to answer is the time, how much we need to expose, basically, because glass transition is just one number, right? We need to figure out the time it requires to be exposed to sort of get to that temperature. Of course, it's not doable for a plastic sheet to measure its temperature at all the points. And we better, when we have a lamp, let's say heating lamp, we find the time. So if I, let's say, write down the change in temperature with time, like the basic knowledge that we learn in maybe heat transfer. So the change in time with time, we can say it's equal to the amount of heat we give to a material multiplied by area divided by its mass multiplied by its heat capacity. All right. So then the change in temperature as a function of time, we can quantify it as the amount of heat we are giving it, Q multiplied by A, its area, and then divided, of course, because it's going to be a ratio of its mass and multiplied by the heat capacity. The bigger the heat capacity, of course, and then the bigger the mass, is going to take longer to get to a desired temperature. So Q, we just learned that, let's say if I'm using a heating lamp, is equal to P multiplied by A, and then we have A there. For mass, I can write down rho, the density, and multiply by the volume, and volume for a plastic sheet is A multiplied by H. H is the thickness of the plastic. So this one then is area, of course, and H is the thickness. All right, and again, remember, we are talking about a plastic sheet. So that's the geometry we're talking about. Rho is the density, and Cp is a constant, depends on the material. So let's see what I got. I can simplify it to P, A, and then over here I have rho, H, Cp, which all of them are constant. So I can do the integral easily, right? Let's say if I do the integral, or let me simplify it one more step. I can write down dt is equal to this constant rho A, sorry, P A rho H Cp, and then dt. All right, now let's integral, okay? If I integral the temperature, let's say I want to get from the room temperature to the glass temperature. All right, so then keep in mind, this is the room temperature. And this is the glass transition temperature. And the other side of integral, it is time 0 to, let's call it the time for forming. The time that we can form the plastic. Luckily, everything is constant here, and it makes it super easy for us. Then if I simplify it, I will get T form equal to rho H CP PA TG minus TR. And another key formula for thermoforming we should know. Let's put it inside the box. So we know this is a key formula that we need. All right. So let's say we start with the material that we want, ABS. So we know what is A. It's absorption coefficient, because for the type of ABS, the color, the density, we can look it up. Usually when we buy plastic sheet, and there in a specification, we can find this A number. P is the intensity of the lamp that we are using. If we are using a particular thermoforming machine, then we can look at the specification. So we have that number as well. We know the density, the thickness of the plastic sheet that we have, and also CP, the heat capacity. We look up the glass transition, or at least the range that we have, and then we decide for something like, for example, for ABS, we can go for maybe 145. And then we know the room temperature that we are operating. So we can find out then easily how much time we need to expose these plastic sheet to get to the desired or to the form temperature. Also keep in mind that most of the thermoforming process are continuous process. What do I mean by that? It's let's say you're making coffee cup lids. So the sheet is coming with a certain speed, and then they are formed and trimmed to the shape that we want. Again, in one of those videos, most likely you've seen it. That sense, let's say this is, maybe we simplify it. Let's say this is the plastic sheet that I have. And let's say this plastic sheet is moving with a certain speed. Let's call it V feed, or feeding speed. All right. And let's say this is maybe the lamp that I have. So this is the heating lamp. And this heating lamp, obviously, they have a length. And let's say its length is L. All right. So you have your plastic stock moving with a speed, V feed. And usually these things are, let's say, maybe on a conveyor. Like that, and then we have the mold, and then they get to the form that we want. So from this, we can guess if the length is L, and let's say this area is exposed to the heat. If we know the time, then we can estimate the feeding speed, right? This is the heat. We know the exposure time, then easily I can write down L, and assuming the speed is constant, is V feed multiplied by the T form. So I can find out the feeding speed as well. All right. So I guess there is one of the question in assignment 2, which you need to calculate the feeding speed, which you need this formula for that. So very simple. And as you can see, if we have the information, we can easily find the feeding speed and the time, the exposure time. Is there any question, guys, before we move on? No question? Okay, so I assume that it's easy. And then we need to answer the second question. Remember, there were 2 questions, right? The first one, how long do I need to expose it to the heat? And then the second one, how much I can stretch a plastic. Like this cup, again, the bottom that you see here, probably made by polystyrene, and polystyrene has the maximum stretching or this RA, which sometimes people call it the area draw ratio. Area draw ratio. So physically, it means there is a limit that you can stretch it. And it's obvious it's going to tear at some points if you stretch it too much. So this RA defines as the surface area, the total surface area, divided by the surface area of footprint, or the project area. So this one, denominators, it's the projected area. So maybe a better example, let's show it here. On this cup, let's say if this is the mold that I have, so this area is going to be the projected area. Projected area. The rest, we assume that like over here, we assume that they have been clamped area. We don't count them. They have been clamped. So only you can imagine this blue area, this circle is being stretched, right? So this is then the clamped area. The pink one, or the one I wrote by pink, or the one that I highlighted by blue, is the area, the circle that is going to stretch to this cup that we want. So if I call this area, let's say A1, and then for this cup, my RA is going to be let's say, call this one A2 and this one A3. It's going to be total area that has been stretched, A2 plus A3, divided by projected area, which is A1. Let's say, as an example, if we make a cup, maybe radius here 20 millimeters, and let's say the radius here to be 40 millimeters, and let's say the high so let's say the high to be 100. So if I haven't done a mistake, I just did the calculation last night when I was tired. So hopefully I didn't make a mistake and I got the number 4.6. Please do the calculation for this yourself. It requires some geometry, right? It's, let's say if you have a triangle, then in order to calculate the area, you need to find out some numbers, right? So you have like here 40, you have here 80, and then the rest try to do the calculation. All right, so if RA is 4.6, and let's say if I'm using maybe ABS, I'm okay. If I'm using PVC or PP, I'm okay. However, if I'm making a cup with this size, so I intentionally pick these big numbers, and so I wouldn't be able to make it by PS, by polystyrene. So I need to go with a smaller size or maybe a shorter height. Okay, is there any question, guys, so far? All right, guys, so see you on Thursday, and bye for now. All right, have a good evening.